So I hope this serves as a reasonable explanation for what RMS is. Okay, it is a way of providing an average value that makes sense with our experience. That's because saying that the average current and the average voltage in an AC circuit might be true on a mathematical level, but it's meaningless for us. So we want to have something that actually represents the fact that the AC circuit delivers power and it's driven by the squares. So this is the method we use. We get RMS value. So when you see that, you see a 120 volt AC value. Okay. This is your typical, power outlet like that down there. Okay. When you see that 120 volt AC, what that is the 120 volts. This is the RMS value. In fact, if I were to make a graph of the actual output of the power from a wall, like this, I would find that it peaks, it's about 170 volts. It goes between positive 170 volts and like negative 170 volts. Okay, and then of course the average is 0, but the RMS average is 120 volts, which means that it delivers power in the same way as a 120 volt DC power source. Okay, so it oscillates between positive 170 and negative 170, but the effect of how much power it produces is the same as a 120 volt DC power source. So this is that's what we say. We're talking about a wall outlet like this guy down here, 120 volt AC. That's your 120 volt RMS AC voltage. So I hope this helps with there's multiple questions that were asked about RMS, and I hope all that scribbling on the board is useful. One more thing about the RMS. So someone asked another question. I wrote it down and I forgot to talk about it. Someone says, well, then what's the instantaneous voltage? Okay. The instantaneous voltage is what the voltage is at any given moment. So your AC household voltage is oscillating up to 170, back down to 0, down to negative 170, back up to 0, up to positive 170, back to 0. Okay. And we said that like the peak voltage is 170. The RMS and the average voltage is 0. The RMS average is 120. The instantaneous voltage is anywhere it is. If you were just to somehow capture that voltage at one particular moment in time, it would be wherever you are actually on the graph. So it's kind of like if you're driving and you're heading to Lexington or something. It's 70 miles, and let's say it takes you an hour to get there. Well, it could be that you put your cruise control on 70 and you actually just went 70 miles an hour all the way to Lexington and your car never varied. But in fact, what's probably the case is that you actually probably went over 70 at some times. Maybe you even went up to 80. Okay. And other times you had to slow down for traffic, or there's a deer running across the road or something, and you slow down to 30 or 40. Okay, so on average you went 70, but what your speedometer read from moment to moment that's your instantaneous speed, not your average speed. Well, the same thing with your alternating sinusoidal voltage. We know what the max is and what the min is and what the average is and what the RMS average is, but moment to moment, what's that voltage? Well, it could be anywhere between 0, it could be 0, 10, 20, 30, 40, 50, anything up to 170, anything down to negative 170, anywhere along that curve. That's your instantaneous voltage. All right, a couple more questions. Well, someone asked me about phasors. And figure 1129, I want to point out that was not on the section 11.5 on phasors. That was not in your assignment. The trigonometry stuff with the sine and cos, that stuff will That'll be more like a circuits 2 question. All right. Somebody asked if you could run a generator off or an alternator off a hamster wheel. Have a hamster running in the wheel and have that run the generator so that the hamster is your power source. And the answer to that question is yes, you could run a generator off of a hamster wheel. It could only generate as much power as the hamster could produce. Okay, you know, if you remember that crank generator, now I wish I'd gone over to the lab to record this instead of here. You remember that crank generator that we had? I had people, you could hook up more lights to it. You could feel it load up, right? When you have more, you know, to produce electricity requires work. Work, you know, you have to have force, and you have to have, like for a generator, a torque. Remember with motors, power output was a torque and a speed. I did an example on that in the last class. You have more torque, more speed, more power. It goes the other direction too. If you want to generate power, you have torque and speed. So, you know, the faster you crank the motor, the generator, the more oomph, the more electricity gets generated out of it. And also the harder it is to turn. Well, if you load up something on a generator, it'll actually take torque, twist to make the generator turn, as you're shoving that electricity through the circuit. So if you have a little hamster on there, you know, the hamster can't generate much torque, right? And maybe you can gear it way down, in which case the hamster can't generate much speed. But, you know, so yes, you can have a hamster generate electricity, but you can't have a hamster generate much electricity. Okay, so now I'm going to do some of the example problems people asked about. The question that got the most requests was example 11.7. Okay, so 11-7. This had to do with converting degrees into radians. Now, in a circle, right, we say there are 360 degrees in a circle. Now, where did the 360 come from? The 360 comes essentially out of astronomy, that there are 12 cycles of the moon in a year, and each cycle of the moon is 30 days. So 30 times 12 gives 360. So in a lunar calendar, a lunar year has 360 days, and that's where we get the 360 from. In a full cycle, full year, there's 360 days. Now, you're going to say, well, there's 365 1/4. Yeah, that's true. That's on a sun calendar. But for counting moon cycles, there's 12 complete moon cycles in a year. So lunar calendars have their years are off a little bit. Now, where does 2 pi come from? Well, that comes from the idea, that's radians, and that comes from the idea that circumference is 2 pi times the radius. So if I go, this is my radius, if I go all the way around, then my circumference is 2 pi times the radius. If I go halfway around to here, then this circumference would be 1/2 of 2 pi times the radius, which is just pi times the radius. So your circumference is pi times the radius for half a circle, 2 pi times the radius. And so we see that there's a correspondence between pi and the degrees, that pi corresponds to 180 degrees, where pi is radians. So your conversion factor is this. Pi is 180 degrees, pi radians. So, so the example that says convert 60 degrees to radians. So 60 degrees, and then you put what I want to get rid of on the bottom, that's 180 degrees, so that the degrees cancel out. What I want to keep is pi. So I cancel these, all right? And so now I got 60 over 180 times pi, and that is going to be 3 times 60, 2 times 60 is 120, 3 times 60 is 180, so this is 1/3 pi, okay? And then it says convert pi over 6 to degrees. So if I have pi over 6 radians, then what I want to get rid of from the bottom is pi, and 180 degrees is on the top, right? This is the opposite. I'm turning degrees into radians. Here I'm turning radians into degrees. Obviously the pi's cancel out, and I end up with 180 degrees divided by 6. Well, 18 over 6 is 3. Okay, so this is 30 degrees. So that makes sense. 60 degrees is a third of pi. This is pi over 6, which is half of a third of pi. So the answer should be half of what the previous answer I had was 60. So then the next question was convert 15 degrees. This is a related problem. To convert 15 degrees to radians. So 15 degrees times pi over 180 is going to be 15 over 180 pi, and I'm trying to do this in my head, so let's say I can divide 3 into both of these. So 15 divided by 3 is 5, and then 180 divided by 3 would be 60 pi. Oh, and then 5 will go into 60 12 times, so that's 1/12 pi. Okay, so 15 degrees is 1/12 pi. I'll check my answer in the book in a minute. And then the next one is 5 pi over 8 into degrees. So 5 pi over 8. So now I do 180. I want to change it to degrees. So that's 180 degrees over pi. So now I got 5 times 180 divided by 8. So I'm going to use a calculator for this. Come over to my computer. 5 times 180 divided by 8. 112 and a half. So 112.5 degrees. Now I'm going to take a moment to check my answer in the back of the book. And yep, these answers are correct. Okay, so this is example 11.7. Okay, so let me do now the next example. And we're going to do, there's another one people ask about is 11.17.